All right, let's dive straight in. Gambling. It's one of those topics, isn't it? It runs the gamut from, whispers of destiny and lucky charms, all the way to these complex mathematical systems people think can guarantee wins.
Mm-hmm. And what's really interesting is how even, well, really smart people, mathematicians even, have sometimes been fooled by the, let's say, the deceptive logic of chance.
Exactly. It trips people up. That's really our mission today. We're
Mhm.
taking this collection of material you provided on the theory of gambling, statistical logic, and we're going to try and pull out the key insights.
Yeah, the goal is to kind of peel back those layers, move past just luck, and really get at the mathematical and logical core of these games, whether they're pure chance or involve skill.
Right. Understand that sort of mathematical DNA.
Yeah.
And it looks like a pretty comprehensive set of sources, too.
Oh, yeah, it covers a lot of ground, historical perspectives, mathematical formulas, game theory. It's all in there.
And for you, the learner, listening in, this is really valuable stuff. I mean, whether you're dealing with risk professionally or you're just curious about how probability works, or maybe you just want a more informed viewpoint on, well, uncertainty in general.
It applies pretty broadly. So where should we start? Maybe the history goes way back.
Yeah, let's do that. It seems like the urge to gamble is, well, almost primal, right? The source mentions evidence going back to Paleolithic times.
It does. Things like polished knuckle bones, painted pebbles, clearly used for games of chance way back then, long before anyone understood odds.
Amazing. So when did people start actually thinking about chance in a more structured way?
Well, the first real reasoned considerations pop up in the 16th century. There's this incredible figure, Girolamo Cardano.
Ah, yes, Cardano. He was quite the character, wasn't he?
Oh, absolutely. A
Yeah.
true Renaissance man, physician, philosopher, scientist, astrologer, and crucially for us, a gambler. And he wrote this book, Liber de Ludo Alea, book on games of chance. It was really the first major attempt to, organize chance events into some kind of discipline, to put some structure on it.
A groundbreaking effort then. But it sounds like even after him, while other mathematicians looked at card and dice games, it didn't immediately revolutionize probability theory.
Not immediately, no. It took a bit longer for the major leaps. Thinkers like Daniel Bernoulli later on were really key. He brought calculus into the mix to understand risk and what we call mathematical expectation.
Okay.
And he, along with Demoivre, did important work on the limit theorem, which is fundamental in probability.
Now, the source also mentions D'Alembert and some, let's say, interesting ideas he had, like thinking tossing 3 coins at once is different from tossing 1 coin 3 times.
Yes, D'Alembert had some incorrect notions, frankly. That coin example is one. He also fell hard for the gambler's fallacy.
Ah, the classic, I've lost 5 times in a row, I must be due for a win, thinking.
Exactly that. The idea that after a run of heads, tails somehow becomes more likely. It just ignores that each coin toss is independent, a fresh start every time.
Right.
He also had this idea that a really, really small probability was basically zero, which led him to cook up a betting system based on that faulty logic. So while he engaged with the topic, his grasp wasn't always solid.
It's a good reminder, isn't it? Even brilliant people can get probability wrong.
Okay.
Then we get to Reverend Thomas Bayes. The source calls his work revolutionary.
And it really was. His paper on the doctrine of chances, published after his death, laid the groundwork for what we now call Bayesian statistics.
Which is huge today, right? In all sorts of fields.
Absolutely. It's all about updating your beliefs, your probabilities as you get new evidence, hugely influential in science, AI, machine learning, far beyond just gambling.
Okay. And moving forward, we see figures like von Mises and R.A. Fisher pushing for a more statistical sort of operational approach.
That's the key word, operational. They really wanted to define probability based on observable frequencies, on measurement, rather than getting bogged down in maybe more abstract philosophical debates. They aimed for solid mathematical footing.
Got it. Grounding it in data. And around this time, early game theory starts to emerge, too.
Yeah, Borel made an early attempt at a mathematical theory of game strategy back in 1921. Interestingly, it was directly influenced by gambling problems, and he even applied it to contract bridge.
Fascinating. Now, the source also touches on the less glamorous side. Gamblers Anonymous starting in 1947.
Right. It highlights that gambling can become a serious problem for some people, and it also notes a shift in public perception, moving away from glorifying those bet-a-million types.
Like Gates and Rothstein.
Exactly. And that famous phrase, breaking the bank at Monte Carlo, it just meant a table ran out of chips temporarily, not that the casino went bust.
Mm.
A bit less dramatic than it sounds.
Huh, okay. So a really rich history there, deeply intertwined with math. Let's shift now to the philosophical side. The very idea of probability seems, well, contested.
It really is. The word itself comes from Latin probabilis, meaning truth resembling, which already hints at ambiguity. Philosophically, people debate what probability even applies to.
Like, can you talk about the probability of rain tomorrow in the same way you talk about the probability of rolling a 6?
Exactly. Or the probability of a certain candidate winning an election. Or even a unique historical event, like the source uses the example of Cleopatra seducing Antony. Can we assign a number to that?
That's tricky. What about one-off events, like this specific poker hand being dealt right now, or something seemingly determined, like is my wallet in my pocket? Does probability apply there?
These questions highlight the different schools of thought. The frequentist view, for instance, defines probability based on long-run frequency. Flip a coin millions of times, the probability of heads is the proportion of heads you observe in the limit.
Makes sense for repeatable things like coin flips or dice rolls. What about the classical theory?
The classical theory is probably what most people think of first. It's the ratio of favorable outcomes to the total number of equally likely possible outcomes.
Like one favorable outcome rolling a 3 out of 6 total possibilities on a fair die, probability 16.
Precisely. But its weakness is, what if you can't easily determine or assume all outcomes are equally likely? Or if the number of outcomes isn't finite?
Right. And there's also a logical theory mentioned.
Yeah, briefly, the logical theory or degree of confirmation sees probability as how much evidence supports a statement. It's more about logical relationships than empirical facts, so it's often considered less relevant for, practical gambling problems.
But here's the interesting thing. Despite all these philosophical disagreements about what probability is, everyone seems to agree on how to calculate it, right? The math works.
That's largely true. The calculus of probability, the mathematical rules and formulas, is built on a consistent set of axioms. It functions like a logical system, like geometry. Given certain assumptions, axioms, these are the results, theorems. So mathematicians can agree on the calculations even if they disagree on the deep meaning.
Okay, so let's get into that calculus. What are some key tools relevant to gambling? The addition theorem first.
Right. The addition theorem is for mutually exclusive events, things that can't happen at the same time. Like drawing a single card that's both a heart and a spade. Impossible.
Okay.
So the probability of drawing either a heart or a spade is just the probability of drawing a heart plus the probability of drawing a spade. You just add them up, PA or B plus PB.
Simple enough. What about the multiplication theorem? Sounds more complex.
It deals with the probability of two or more events happening, potentially one after the other or together. This brings in conditional probability.
Conditional probability. That's the probability of something happening given that something else has already happened.
Exactly. PBA. Probability of B given A. The general multiplication rule is PA and B equals PA, PBA. Think about drawing two cards without putting the first one back. The probability of the second card being an ace depends on whether the first card was an ace.
Right, because the deck has changed. Got it. The source also brings up permutations and combinations. Always good to get a clear distinction there.
Yeah, they often get confused. Permutations are about arrangements where the order matters. Think of arranging books on a shelf or the finishing order in a horse race. How many ways can the top 3 finish out of 10 horses? That's permutations, NPR.
Okay. Order matters for permutations.
Combinations are about selection where the order doesn't matter. Think of dealing a poker hand. It doesn't matter in what sequence you receive your 5 cards, the final hand is the same. That's combinations, NCR.
That's a helpful way to put it. And obviously crucial for calculating odds in card games, lotteries, dice rolls.
Absolutely. And related to these are specific probability distributions mentioned in the source, like binomial, geometric, and hypergeometric.
Right. What's the gist of those?
They're like templates for specific kinds of random processes. The binomial distribution applies when you have a fixed number of independent trials, each with 2 outcomes, like success, failure, heads, tails, and the probability is the same for each trial.
Like flipping a coin 10 times and asking the probability of getting exactly 7 heads.
Perfect example. The geometric distribution is different. It tells you about the number of trials needed to get the first success. Like how many times do you have to roll a die until you finally get a 6?
Okay, first success. And hypergeometric. Sounds fancy.
It's used when you're sampling without replacement from a finite population. Imagine drawing 5 cards, not putting them back, then drawing another 5. The hypergeometric distribution helps calculate the probability of, say, having exactly 2 cards in common between those 2 hands.
Ah, so it accounts for the changing probabilities as you remove items. Makes sense.
Hmm.
And then briefly, maximum likelihood estimation and students' t-distribution,
Hmm.
more advanced stats.
Yeah, maximum likelihood estimation is a technique statisticians use to find the parameter values for a distribution that best explain the data they've actually observed, sort of working backwards from the data.
Okay.
And students' t-distribution is really important when you're working with small sample sizes and you don't know the true standard deviation of the whole population, useful for analyzing limited runs of a game, perhaps.
Wow. Okay. A serious toolkit there. Let's switch gears a bit to game theory. This feels like where strategy really comes to the fore.
Definitely. Game theory is the formal study of strategic interaction. It analyzes situations with multiple players making choices where the outcome for each depends on the choices made by all players.
So you've got players, their possible actions or strategies, and the payoffs, usually money in gambling.
Right. And a key distinction is between zero-sum and non-zero-sum games.
Okay, what's the difference?
Zero-sum means the total gains equal the total losses. One player wins exactly what another player loses. The net change in wealth is zero. Think of a simple heads-up bet.
Okay, and non-zero sum.
That's where the total payoff for all players can change. It can increase or decrease. A classic example in gambling is a poker game where the house takes a rake from each pot. The total money among the players decreases over time. Or, conversely, some cooperative games could be positive sum.
Got it. And strategies can be pure or mixed.
A pure strategy is deciding on one specific action and sticking to it. Always bet on red, for example. A mixed strategy involves randomizing your choices according to certain probabilities. Like deciding to blush 30% of the time in a particular poker situation, it makes you less predictable.
Right, keeps your opponent guessing. So if players are using these mixed strategies, how do you figure out the likely outcome?
That brings us back to mathematical expectation. You calculate the expected payoff by considering all possible combinations of the player's mixed strategies, figuring out the payoff for each combination, and then weighting each payoff by the probability that that specific combination of strategies occurs. It's a weighted average of all possible outcomes.
And the goal is usually to find the optimal strategy, right? The best way to play.
Exactly. In many games, especially competitive ones, you're looking for optimal strategies, often mixed strategies that maximize your expected payoff, assuming your opponent is also playing optimally. The value of the game represents this expected payoff when everyone plays their best.
The source mentions the minimax principle too. What's that about?
Minimax is a way to define a best strategy by focusing on minimizing your potential losses. You look at the worst possible outcome for each strategy you could choose, and then you pick the strategy where that worst outcome is least bad. You minimize your maximum risk. It's a conservative approach.
Okay, minimizing the worst case scenario. Now, a really interesting concept the source stresses is utility. Why is that so critical in understanding gambling?
Because money isn't everything. Or rather, the value of money isn't linear. Utility is about the subjective satisfaction or value a person gets from an outcome. Winning $100 means a lot more to someone struggling than to a billionaire.
Right, the happiness boost isn't proportional to the dollar amount.
Precisely. A theory of gambling that only looks at expected monetary value misses how people actually feel about risk and reward. Utility theory tries to capture these preferences.
So it tries to formalize preference,
Yeah.
saying you prefer option A to option B.
Yes, and it's often based on a few core assumptions or axioms. Things like transitivity, if you like A more than B, and B more than C, you should like A more than C. Makes sense.
Yeah.
And substitutability, if you're indifferent between two prizes, you should be okay swapping one for the other in a lottery ticket. And monotonicity, basically, more of a good thing, is better. If a gamble gives you a higher chance of winning something you want, you should prefer it.
And the source mentions something interesting about the shape of utility, how it changes with wealth.
Yeah, the idea is that for most people, the utility curve for wealth isn't a straight line. When you have little money, each extra dollar adds a lot of utility. The curve is steep or concave. But as you get richer, the extra utility you get from each additional dollar tends to decrease. The curve flattens out.
Diminishing marginal utility.
Exactly. And for losses, it might be the opposite. Losing the first $1,000 might hurt more than losing the millionth $1,000, relatively speaking. The shape of this curve explains things like risk aversion, why people buy insurance, and why the St. Petersburg paradox is, well, a paradox.
Okay, utility is key. Let's talk betting systems. The martingale, the double-up strategy. Everyone's heard of systems like that. Do they
Yeah.
actually work?
Betting systems. They're strategies for deciding how much to bet based on past results. You've got positive progressions, increased bets after wins, negative progressions, increased bets after losses, like the martingale, additive systems, logarithmic, fractional, all
The
sorts.
martingale's the famous one, right? Double your bet after every loss.
Yeah.
You eventually win, recover losses, and make a small profit. Sounds good.
It sounds good in theory, but it has two massive flaws in practice. One,
Hmm.
you need a potentially astronomical bankroll.
Right.
A string of losses, which is entirely possible, makes your required bet size explode very quickly. Two, casinos have table limits. Eventually, you'll hit the limit and won't be able to double your bet anymore, locking in a huge loss. And fundamentally, as theorem I in the source material states, no betting system can alter the underlying negative mathematical expectation in a game like roulette. The house edge remains. The system just changes the distribution of wins and losses. Lots of small wins punctuated by occasional catastrophic losses.
So it's just rearranging the deck chairs on the Titanic, mathematically speaking.
That's a pretty good analogy, yes.
Mhm.
The Labouchere system, another one mentioned, is an additive system. It's a bit more complex, involving crossing numbers off a list. Same issue, though, doesn't beat the house edge.
Okay. But what about the Kelly criterion? The source presents that differently, more about maximizing growth rate.
The Kelly system is different. It's not really about trying to beat a negative expectation game. It's a formula derived from utility theory that tells you what fraction of your bankroll to bet when you believe you have a positive edge, a genuine advantage.
So it assumes you have an edge, maybe through superior analysis or information.
Correct. The goal is to maximize the long-term rate of growth of your capital, balancing risk and reward optimally when you do have an advantage. It's used more by sophisticated bettors and investors.
Okay, that makes sense. So systems don't magically create profit from nothing. Let's revisit mathematical expectation and variance quickly.
Sure. Expectation, as we said, is the long-run average outcome. A fair game has zero expectation. Positive is good for the player, negative is good for the house, or whoever has the edge.
And you can calculate expected gain over many plays just by multiplying the single play expectation by the number of plays. What about variance again?
Variance measures the spread of outcomes. How much do the results swing around the average? High variance means you can have big wins and big losses, even if the average expectation is only slightly positive or negative.
Which matters a lot for bankroll management, right?
Mhm.
High variance can wipe you out, even if you have a slight edge long term.
Precisely. Variance dictates the risk of ruin, especially with limited capital, which leads into...
The gambler's ruin problem. Sounds ominous.
It is, kind of. It's a classic probability calculation, looking at a gambler with finite money playing against an opponent, like a casino, with effectively infinite money. It shows that even if the game is fair, or even slightly in the gambler's favor per bet, if they play long enough against a much richer opponent, the probability of them eventually going broke gets very, very high.
Sobering. Okay, let's look at statistical analysis of games. Can we actually use stats to spot things like biased coins or dice?
We can certainly try. If you suspect a coin isn't fair, you can flip it many, many times. Then you use statistical tests, like comparing the observed heads-tails ratio to the expected 50-50 using the binomial distribution or approximations like the Laplace-Gauss theorem. If the observed result is extremely unlikely to happen by chance with a fair coin, you might conclude it's bias.
Like those huge coin-tossing experiments by Karich and Pearson the source mentions.
Exactly. They generated massive data sets to study randomness empirically. You can do similar analyses for dice, checking if all faces come up with roughly equal frequency over many rolls.
What about runs? Like getting 5 heads in a row, does that mean anything statistically?
Well, random sequences naturally contain runs. We can actually calculate the expected number and length of runs in a sequence of a given length. If you observe wildly different numbers of runs than expected, it might hint at non-randomness. But individual long runs are perfectly normal in random data. Our intuition often misleads us there.
Right, we see patterns everywhere, and the one-dimensional random walk, how does that model gambling?
Think of your fortune going up or down by 1 unit with each bet, win or lose. That's a random walk. One counterintuitive result mentioned is the arcsign law. It suggests that in such a walk, you're most likely to spend the vast majority of your time either significantly ahead or significantly behind your starting point, rather than hovering near break-even.
Huh. That is counterintuitive. You'd think you'd cross the starting line more often.
Yeah, our intuition often expects more fluctuation around the mean than actually happens in a true random walk.
Okay, fascinating. Let's apply some of this to specific games. Coin matching.
Simple game. Two players show heads or tails. Payoffs depend on matching or not. If it's symmetric, same win-loss for match mismatch. The optimal strategy is usually 50-50 random choice for both a mixed strategy, expectation 0. But if the payoffs are asymmetric, or one player knows the other's bias.
Then you can potentially exploit that. What about bluffing games, like the coin example in the source?
Game theory shines here. One player has hidden info, the coin flip. The other has to decide whether to trust their claim. You can mathematically derive the optimal bluffing frequency for the first player and the optimal calling folding frequency for the second player to reach an equilibrium.
Where neither player can improve their outcome by just changing their own strategy.
Exactly. And you can calculate the value of the game, the expected outcome when both play optimally.
Okay. And the St. Petersburg paradox. I know the setup: flip a coin till tails, pay out doubles each time heads comes up first. The expectation is infinite, but nobody would pay much to play.
Why? Right. The expected monetary value is infinite because of the tiny probabilities of incredibly huge payouts way down the line. 2n grows very fast. But again, it comes back to utility.
Diminishing marginal utility of wealth.
Precisely. The subjective value of winning billions is not billions of times greater than the value of winning a few dollars. Our utility curve flattens out. We're just not willing to pay enormous amounts for those incredibly remote chances of astronomical wins. Plus, any real-world game would have a finite house bankroll capping the maximum payout anyway.
That makes sense. Utility solves the paradox. And the source briefly mentions the two-armed bandit problem and political campaigns. Just showing the breadth of game theory.
Yeah, the two-armed bandit is about exploration versus exploitation, trying out different options, slot machine arms, to see which is better versus sticking with the one you think is best. Big in machine learning. And the campaign example just shows how game theory models resource allocation in competitive scenarios.
Cool. All right, let's hit the casino floor, metaphorically. Roulette.
Roulette. Elegant game, simple bets, and a guaranteed negative expectation for the player on pretty much every bet because of the 0. And 00 in the U.S.
So red, black, odd, even, single numbers, all have a house edge.
All built in. That 0 pocket ensures the house wins on even money bets when it hits, and it slightly shifts the odds on all other bets too. And as we said, no betting system beats that edge long term. Detecting biased wheels is theoretically possible with stats, but very unlikely today.
Okay, so enjoy for fun, but don't expect to make a living. Slot machines.
Slots are pure negative expectation machines, designed to take in more than they pay out overall. The appeal is the simplicity, the flashing lights, and the chance of a huge jackpot, however remote. The only way to beat them legitimately would be exploiting mechanical defects, which is not really feasible now.
And lotteries. Big dreams, tiny odds.
Generally, yes. Very low expected return, often less than 50 cents on the dollar. You're paying a lot for a very, very small chance at a life-changing sum. The source mentions examples like the Irish sweepstakes, historically known for poor returns.
Okay, card games. The source talks about shuffling first.
Yeah, the idea of a fair shuffle. It actually takes quite a few good riffle shuffles, maybe 7 or more, to get a deck close to truly random. Fewer shuffles can leave clumps of cards or traces of the original order.
Interesting. So maybe not as random as we think after just 1 or 2 shuffles.
Potentially. And then, of course, calculating probabilities of specific hands is core to games like poker.
Right. Poker, blackjack, bridge are mentioned.
Poker is that classic mix of chance, the cards dealt, and skill, betting, bluffing, reading opponents. Blackjack is interesting because optimal strategy, basic strategy, significantly reduces the house edge, and card counting can, theoretically, give the player a slight edge.
So casinos don't like card counters.
Not at all. They actively watch for it. And bridge is different, again, a game of partnership and imperfect information. You use probability and bidding conventions to deduce what cards your partner and opponents likely hold.
So more skill involved in those card games, but still fundamentally based on probability. What about games where skill is even more dominant?
Right. The source mentions games like tic-tac-toe, which is fully solved, a draw with perfect play, then more complex versions. Nim is fascinating, a game of taking objects from piles, which has a complete mathematical theory based on binary numbers to find winning moves.
Wow.
Hex is another, played on a diamond grid, where the first player has a proven winning strategy, though it's hard to execute perfectly. And things like pursuit-capture games model strategic movement.
And these ideas feed into wargaming economic models.
Absolutely. Game theory provides tools to analyze competition and strategy in many complex real-world systems. Even early attempts at computer chess and checkers were pushing the boundaries of implementing strategic logic.
Okay, but strategy and math aside, there's the whole psychological side of gambling, isn't there? Our brains seem wired in funny ways.
Very much so. We fall prey to all sorts of biases. The gambler's fallacy we mentioned, thinking past results influence future independent events, believing in hot streaks or feeling due for a win. The Monte Carlo fallacy is basically the same thing, seeing red come up many times and thinking black must be next.
Our pattern-seeking brains working overtime.
Exactly. And there's a documented gap between psychological probability, how likely we feel an event is, and mathematical probability. We tend to overestimate our chances of desired outcomes, like lottery wins, optimism bias.
Which can lead to poor decisions, clearly. Finally, the source tackles ESP and gambling, a controversial link.
Yeah, the idea that you could use extrasensory perception, telepathy, clairvoyance, maybe even psychokinesis, moving objects with your mind to win at games of chance. People like J.B. Ryan did experiments on this back in the day.
Card guessing, influencing dice rolls.
But the source brings a critical lens, referencing David Hume's argument about miracles.
The idea being that extraordinary claims require extraordinary evidence.
Precisely. Is it more likely that someone genuinely has psychic powers that defy known physics, or that there's an issue with the experiment, maybe subtle cheating, flawed methodology, statistical anomalies, or just selective reporting of results?
And there were mathematical critiques of these ESP experiments, too.
Yes. Focusing on whether the statistics properly distinguish prediction from chance guessing, controlling for sensory leakage, potential biases in targets, or recording, when experiments were done under really stringent conditions like total sensory isolation for telepathy.
The results tended towards chance expectation.
Often, yes. That's what the source suggests. The evidence for ESP reliably influencing gambling outcomes remains highly contested and generally unaccepted by mainstream science.
Okay, so maybe leave the crystal ball at home.
Probably wise.
Well, this has been incredibly thorough. We've gone from ancient knucklebones to modern game theory. What's the big takeaway?
I think it's that gambling is this fascinating crossroads of math, probability, statistics, strategy, and psychology. Luck certainly determines individual outcomes, the next roll or the next hand.
Right.
But understanding the underlying principles, the expectations, the variances, the strategies, the psychological traps gives you a much clearer, more informed view of what's actually going on. It lets you see beyond just good luck or bad luck.
Absolutely. So for you listening, think about how these ideas, probability, expected value, risk assessment, even psychological biases might show up in your own life. Decisions at work, investments, even just everyday choices involve uncertainty.
The principles are surprisingly transferable.
So maybe the next time you hear someone talking about being due for a win or having a foolproof system, you'll think a bit differently about the math underneath it all.
Indeed. And perhaps a final thought to leave you with. Beyond the obvious games, where else in your life are you implicitly placing bets based on perceived odds and potential payoffs? And could a more explicit understanding of probability and utility lead to better choices?